Hello, we're going to continue talking about how to analyze more complicated circuits with some methods. One of them is the mesh analysis, and another one is the nodal analysis. We mentioned that complicated circuits involve different sources, such as more batteries or sources of voltage. They can also have sources of current, and the first thing you need to do is you need to identify the closed loops. So in this circuit we have two closed loops, one and two, and it's because this is a whole closed loop and this is the other closed loop. Okay. You can have three, four, many closed loops. This one is the typical closed loop for bridge. We'll talk about those circuits in a little bit, and they're independent loops. So that's the first step. So let's go over the example right here. We have a circuit that has one battery or one source that is 2 volts. Then it's connected to our resistance that is 2 ohms. We have point A, point B, point C, and point D, which are point A is the maximum potential. This is the maximum voltage. Point B is going to be type of a voltage divider here. It's going to be the voltage right after the source. We have ground, which is always going to be voltage reference. We have point D, which is also between those two elements, the battery and the resistor. The second loop is this loop right here. So this is loop number one, this is loop number two. By convention, you choose the nodes that have the highest potential. So A is a very good suspect to start analyzing. All right, so they're asking what is the current through leg 1, 2, and 3. So this is the current. All this right here is current I1. All this right here is current I2. And the current through this branch is current 3. Okay. So if, for example, you have this configuration, remember that we can turn this setup into a similar setup with a source of current in parallel with the resistor. This is going to be the same value resistor, and the value of the current is simply found by Ohm's law. So V equals IR. So I equals V over R is 2 over 2. 2 volts by 2 ohms equals 1 amp. So this is 1 amp. Place the resistor in parallel, 2 ohms, and then we have the same thing. So this is pretty simple because we can have set of resistors in parallel, such as in this case, the current is going to add up. Remember that the current in series is the same, but in parallel is different. So since this current source is in parallel with this current source, we can have a total current of 6 plus 1, 7 amps. So in that case, we have a single current source, which is this guy. And then we can get the parallel resistors of the source, which are 2 and 1. You find the total of the equivalent resistance of those resistors. We're talking about this resistor and this resistor. And the equivalent resistance of that is 2/3. Okay. So now we have two resistors in parallel. In that case, it's pretty simple because we already know how to use the current divider rule, and we can look at the formula, and it's going to be the total current is going to be the source 7 amps times the current parallel to the source divided by the total resistance of the elements. So say it again, the current I, and which one is that? Is the one going through this 4 ohm resistor. In other words, it's current 3, I3. If you remember, this was I3 right here. So I3 will go through the resistor, and to find that current, we need to multiply the source times that resistor, so 7 times 2/3, divided by the summation of that resistor plus the other resistor, of both resistors basically. And that gives us 1 amp. So the current through here is 1 amp. Okay, and in that case, it's simpler to go ahead and find I1 and I2, but this is just showing the point of starting to use different methods to analyze the circuits. From here, it was simpler to go this way because we can do the equivalent resistance of the circuit, and then we can do the current divider rule here. In other words, we cannot do the parallel resistance of, we cannot find the equivalent resistance of everything because this current here is not the same as the current from here and here. Those two currents can add up, but we don't know this current here. So that's why, since this is from the source, we can make that in parallel with this one by adding the sources. Okay, so look at this example again. Um, remember how to use the current divider rule, and remember that it's pretty important to identify the current through the loops. Okay, so if they ask about I1 and I2, well, we already know that in this particular case, I1 plus I2 plus I3 equals 0, and we already know that this is I3, so we can go ahead and do Ohm's law in other places and find I1 and I2. So in that particular case, um, we would have to analyze the loops independently if we wanted to find I1 and I2. So this is the next step to solve for voltages in a more complicated circuit. This is the same circuit from before, but now they're still wanting to find I3, I2, and I1. And what we're gonna do is, instead of going through the source equivalence, converting this guy to the current and resistor, and this one to a current and resistor in parallel, we're gonna use the method of mesh, or the mesh method. And it's basically setting up an equation for each loop, always trying to keep the contacting elements as the coupling terms. So the only term that is in contact with this loop and that loop is resistor number 3. So if they're wanting to find three electric currents, I1, I2, and I3, we need 3 equations. So we're gonna find how to create those equations. So this is loop number 1, and this is loop number, which one is loop number 1? I1 and I3. Yes, this one is 1. Loop number 2 is this one. So let's go ahead and see how we set up the equation. So we already said before that I1 plus I2 plus I3 is equal to 0. What is the value of I1? Well, at this point we don't know any of them. Before we found I3 by going to the equivalent source, but at this point we're not going that route. We're gonna use another method, so practically assume that we didn't find I3, or we don't know what I3 is. We're gonna use a completely different method. Okay, so the next thing we need to do is set up the equation for conservation of voltage. So that equation says that V1 plus V2 plus V3 is equal to 0. And that is because we have a voltage through this branch because of the source, a voltage through this branch because there's no source, and a voltage through this branch because there's a different source. So even though these elements are set in parallel, this is not a common parallel circuit because a parallel circuit only has one source and everything else is in parallel. In that case, the voltage through each branch, through each leg, is the same as the source. In this case, is not that same scenario. So we have that the conservation of charges will tell you I1 plus I2 plus I3 equals 0, and V1 plus V2 plus V3 equals 0. So what we're going to do is we're going to set up the equations to find the current. So notice that Ohm's law is I times R. So let's go ahead and set, you have two options here. You can set up the equations to solve for current, or you can solve for voltage. So in that case, it's really depending on what you want to have expressed. If you want to solve for current, then you need to put your equation in terms of I times R. If you want to solve for voltage, you know, put your equation in terms of V over R equals I. So in that case, you will be solving for voltage because the resistance is usually known, since you're designing a circuit with known resistances. But furthermore, since we have values of voltage, we want to use known values of voltage. So let's go ahead with this equation because we have some of the voltages and then some of the other voltages will be unknown, versus here all the currents will be unknown. So let's set up the voltage equation and then start it right here. So loop 1 is this loop right here, and we're gonna go through all the voltages. So where's the rise in potential? Right here, because it's a voltage source, and it's gonna be E1, so 2 volts. Then some of the power is going to be used for this resistor, so it's going to be a voltage drop. Therefore, there's going to be minus the voltage drop through here, and that voltage drop is the current times the resistance. So that is basically minus the voltage drop through resistor 1, and then there's going to be also voltage drop because it's going to ground, and there's no source near it. Therefore, that's negative voltage drop. So in other words, for this equation to be true, the conservation of charge, which should be true always, you the only term when you start is from the source. The source is giving you power and every other element is using power. So E1 minus the voltage drop here minus the voltage drop there is equal to 0. Use now the second loop. Okay, very nice. In that case, what we need to do is look at, in this case, we went from this point down this resistor. So if we go this way, we're gonna go down the resistor, which is not the case. We wanna go from that point around and go up the resistor. Why? Because we want to be having this resistor as the coupling element. So on one loop will go down to ground and the other loop will go up to have this resistor be the coupling balancing element. So that's one rule of thumb. So if you set up the equation for that, you will have that since it's going up, then you're having a potential at point A, and it's going to be the voltage drop through resistor 3. Yes. Then voltage drop of resistor 1 is going to be a positive 1. Yes. Why? Because now we're going to use this as a sink. Basically, it's going to take all the power away. So this is we're kind of cheating a little bit in terms of the practical or the real case where a source is always giving you power. But in order to analyze this, we're gonna decide that no, we're gonna use this two resistors as the one giving us power, and then we're gonna use the battery as the sink, basically consuming all the power. Why? Again, because we need to use this resistor as the coupling element. So if you went here, that if you on this one you decided to go where the resistor is taking element power away with a minus, then on the next loop this will give you power. And that's why we have plus VR2, because VR2 also give us power, and then the battery will take all the power away, minus E2 equals 0. So if you set up the equations, you have for loop 1, you have the source is 2 volts minus the voltage drop through R1, which is 2 ohms times current 1, which we don't know current 1. And then for resistor 3, we don't know the current 3, but we know the value of the resistance, so 4 ohms and current 3. Now for the second loop, we have that 4 ohms times current 3, positive, and 1 ohm times current 2, which we decided is going to be positive also, then negative 6 for the source, equals 0. If you don't follow this artificial, fictitious concept convention, you'll get wrong currents. You get much higher currents that they usually should be. So I'm sure that you've seen this in algebra before, how to set up this as a system of equations. You have three currents and you have three unknowns. You have I1, I2, and I3 as unknowns. So in order to set up this equation, you simply find all the terms that are um, similar. So in that case, let's go ahead and take this. First, let's try to put I1, I2, and I3 equals to the independent terms. So I1 is going to be negative 2, I2 is 0, and I3 is negative 4, and then independent term is equal to, then take this to the right hand side, negative 2, right? Yeah, so negative 2, 0, 4, negative 2, good. And then we have the second term, which is I1 is 0, I2 is positive 1, I3 is positive 4, and positive 6, because it goes to the other side of the equation, right hand side. And then we have two equations and three unknowns, because we're solving for current. Well, the third equation is always going to come from your node that you find with your maximal potential. And this is an important part because we're going to say that this current right here, I1, right here, I1, plus I2, sorry, plus I3, which one is I2? This is I2 and this I3. Yeah, plus I2 equal to I3. Why? Because the current is also coming from the source, and there are two sources. So this current here and the current from this source is being consumed by, is traveling, both currents are traveling through this leg, which is the current I3. So in other words, at point A, we have the current from I1, the current from I3, sorry, the current from I3 is equal to the current through I2. Okay, setting up this incorrectly. There you go. So these two go to the node A and then they're going out I2. Let me do that again. So it's going to a point A and going out. I1, I2, I3. I1 and I2 meet at A and then I3. Okay, now we have the third equation, which is I1 plus I2 equals odd I3. Oh, but hold on a second. This is not true because we said that I2 was going to go through this branch like that. So that is actually not true. My bad. So please give me a second here. I'm gonna put my A again. And let's do this again. So my A1, this is an important one because if the signs are incorrect, your answers are not gonna be correct. Okay, so my I1 is gonna go towards the node. Yep, that is something that we already did. So towards the node. And I2, so I3 first, because we're going this way, like that. So I2 is going outside the node, and I3 is coming to the node. I2, I3, I1, sorry, and I3. And by convention, the currents going out from the node, outwards, are positive, and the currents going into the node are negative. So I2 minus I1 minus I3 equals 0, or we can change that into multiply times -1, I1 minus I2 plus I3 equal to 0. Okay, so we have a good. So now for the third equation, we have a +1, a -1, +1 equal to 0. And that's what we have here. So it's three equations, three unknowns, where just check this out. If you're not familiar with linear algebra, it's just basically solving for the equation that -2I1, 0I2, 4I3 equals a -2. Then 0I1, 1I2, 4I3 equals 6, and I1, -I2, and I3 equals 0. You solve this equation by hand or using a calculator or using linear algebra. As I said, you just invert this R matrix, and at the end, the solution is this. I1 is -1, I2 is equal to 2, and I3 is equal to 1. And before, we were able to find I3, which is equal to 1. So those answers should match. I3 equals 1 with this method and with the previous method, because the circuit is the same. So to recap, when you use the mesh analysis, you always have one equation given, which is the summation of currents at a node. And all you need to do is set up your equation of voltages so you have all the unknowns, as many equations as unknowns. So we have three currents and three voltages. We need three equations. One equation comes from one mesh, one loop. The other equation comes from the next loop, and the third equation comes from the conservation of charge. So the only difficult part here is realizing which direction we should keep the loops. So that was the mesh analysis. The other method, which it's really up to you which one you use. You can use either method anyway. But the nodal analysis has a few key steps. And it's similar to the mesh analysis in this sense. The number of equations required to solve all the voltages is one less than the number of independent nodes. So before it would be the mesh, we have two meshes, we have one more equation. So if we have two loops, we have three equations. When you do the nodal analysis, depending on all the number of nodes, you have one equation less. So the procedure is the same. Determine the number of nodes within the network. This is easy. Pick a reference node, usually is the maximum potential. So this one is going to be usually the maximum potential, maximum voltage node, so the one on the very top. Apply conservation of charge, Kirchhoff's law, and solve the equations. Okay, so for example, here we have a circuit with a source that is 24 volts, source of voltage, a source of current, which is 1 amp, and the resistors. So in this case, you can do the same thing. You can convert this branch to an equivalent resistance of a source in parallel with a resistor. Now you have the 12 ohm resistor, which is this one, and then you have the current, and then connect them. You can do something similar there, but you can also use the nodal analysis. Um, and the nodal analysis is pretty simple. You choose your maximum voltage node, which will be right here, this node, which keep in mind that even though that's your node, all this branch has the same potential, V1, even though you chose that node. And all this branch has the same potential, which is common, that was 0. All right, so that's the first step, choose your nodes. So we have two independent voltage nodes. Right here, there's V1 and then your ground. You always have to find those. So if you go ahead and notice how many currents we have, we will have I, or the main current is, well, I guess they're using this one, but we're gonna have one current here, one current through here, and one current through here. So there's gonna be 3 currents. Okay, so I2 is the voltage drop through resistor 2 over resistor 2, right? Because this V equals R times I, the evidently I equals voltage divided by resistance. Voltage is this voltage drop, VR2, and the resistance is R2. Okay, so we already know how to find I2, except for we don't have the voltage. We only have the resistance. So we don't have information to solve for current 2 yet. Current 1 is the voltage drop through this resistor. So it's voltage drop through VR1 divided by resistor 1. But notice that the voltage between here and here is not 24 because there's a voltage drop here. The voltage between here and here is 24 plus the voltage drop here. Remember that the voltage through a resistor is always dropping. You cannot have, in theory, the voltage through just a copper wire or conductor is the same. But once you have a resistor, the voltage drops. So the voltage from the source plus the voltage drop equals V1. So in other words, we have V1 equals voltage drop plus E. Okay, so we have information to solve for voltage drop 1. Well, not quite. We have this source, but we don't know what V1 is, which is here at the very top. But at least we have an equation that will relate the voltage drop through resistor 1 and the total voltage from the maximum potential and the source. So current 1 through this leg, oh, this is current 1. Current 1 is voltage drop through 1 divided by resistor 1. So if you put everything together, you'll have that the current from the source, which is 1, they already give you, is I1 plus I2. I1 is this right here, this expression, and I2 is this expression. So put it together, you have the voltage drop through resistor 1, which is the same as this, divided by R1 plus voltage drop through resistor 2, which is V1 minus 0 if you want, V1 minus ground, which is 0, divided by R2. Now, solving for the things that we know this is 1. The only thing here that we don't know is V1. So rearrange the equation to have V1 as a single term, and basically we have that 1 being the source right here. We have that V1 can be solved because we have the value of R1, which is 6, the value of R2, which is 12, and the value of the source, which is 24. So solving that equation, go ahead and use your calculator if you want. V1 equals 20 volts. And notice that since we had 2 nodes, independent nodes, we only had one equation. because the nodes here are not taken as nodes of analysis for the nodal analysis. In order to have a node, you have to have more than two branches bifurcating or breaking. That is just a voltage divider. That will be a good node. This, if you have this configuration, kind of like this is a good candidate for a nodal analysis problem because you have everything that it takes for a node. And here you have the other one. So you have two nodes, and the rule says that if you have two nodes, you have 2 minus 1 or one equation. You have one less equation than the number of nodes. So once you have V1, it's very simple because I1 is simply here. And by solving, you get that the current is negative 0.67 amps or 670 milliamps. And it's negative because we chose the wrong direction for the equations. So in other words, it wasn't I equals I1 plus I2. It was I equals negative I1 plus I2. But doesn't matter. As long when you get this number, you know that it's just that the current actually balancing out towards the different side of the circuit. Instead of coming in or out, it was going the opposite direction. And then with that, you can find I2. So current number 2 is simply voltage 1 divided by R2. And we already know voltage 1 is 20, I2 is 12, so current 2 is 1.67 amps. Okay, so we have the currents and the voltages. So this is a pretty simple approach. Nodal analysis can be very simple if you choose the right node. Another example. Here we have a circuit with two sources, source number 1 and source number 2, 4 amps and 2 amps. But in this case, it's interesting because we have a node right here and a node right here, and they're separated by a resistor. So this is going to be a whole loop, and this is going to be a whole loop, and we're going to try to connect this loop through those voltages. So all this is going to be V1, so up until this point we're going to have V1. All this is V2 up until this point, and we have ground, right, which is connected to all these other nodes. Okay, so the current through here is equal to the current through here plus the current through here. So we already know this. We're always going to have this division of current. So we're going to have that I1 equals, oh, they're calling that I. So, okay, so I not, or I prime, whatever you want to call it, equals I1 plus I3, which is this current and that current. Good. So at V1 we have I prime and I1, I3. I prime is 4. So if we build the equation, it's pretty simple because we know that the potential between here and here is V1 divided by R1, right? So this guy. We're gonna just simply find the currents. Again, use Ohm's law, V equals IR, V1, I1. I1 equals V1 over R1. So this is what we have here. But now the next case is for this resistor, and this resistor is the difference between this potential and that potential. So V1 minus V2 divided by R3, which is what we have. So this equation is already set up. Okay, just rearranging, you have V1 is just 1 divided by 2 plus 1 divided by 12 minus V2, which is this, equal to 4. Oh, but one question is, we have two nodes and two unknowns. So this is going to be an exception here because we have two nodes and we're going to end up with two equations. Huh, Yeah, we're gonna need two equations because we have two nodes, but we have also two different voltages. All right, so in this particular case, I see that we are gonna need another equation. So we already have one equation, which is the equation for this voltage, but we don't have V2, which we need right here. So we can set up the equation for V2 pretty simple. Let's go to this node right here, and we have that the current I3, which is this current right here, I3 plus I2, and I2 is pointing towards ground, so it's going to be coming out of this source. And remember, coming out of the source is a positive current, and this they're giving us this direction already, like maybe they measured it or they know, they give you that this current is going out of the node. So it's I3 plus I2 plus the source I prime prime. Let's call this I prime prime since this is I prime. So I3 plus I2 plus 2 amps equals 0. So let's build this equation. I3 is going to be V2 minus V1, and it's because since it's not V1 minus V2. Okay, so since in this case we're solving for this node right here, V1. So we're gonna start from here. This is our base node and gonna go outwards. So going from V1 and V2, V1 minus negative minus V2. But in this case, we want to solve V2, so it's V2 minus V1. V2 minus V1 divided by R3 is this voltage right here, plus V2 divided by R2, which is this current right here, and I with 2 amps. So we have the current through here, the current through R2, and the current from the source. Now combining the terms, combine the equation from this equation right here, equation 1, and this equation, equation 2, we have 1 and 2. We have two equations and two unknowns. So V1, well, basically the whole equation goes here, and this whole equation goes there. Now we have two unknowns and two equations. We can solve this. So you'll know how many equations you'll need once you know how many voltages are unknown. So in this case, we have two unknown voltages. We're gonna need at least two equations. But for current, you will need three equations. You'll need this current through here, this current through here, and this current through here. So that's why using voltage is a much better approach using the nodal analysis, because it's just the nodes that have the maximum potential, which in this case are V1 and V2. Those will have your equations set up. And simply solving this equation, you can use your calculator or Excel or whatever, just use pencil, and you have the V1 equals 6 volts, V2 is negative 6 volts, and since we have the voltages V1 and V2, we can find the currents just plugging in V1 and V2, and then from Ohm's law, we know that the current, so for instance, the current through resistor 3 is going to be the voltage through resistor 3, which is V1 minus V2 divided by R3. Okay, 1 amp. And the voltage through, and it's the same thing if you do the other way around. If you do V2 minus V1 divided by R3 equal V2 is negative 6. And if you do minus V1, which is minus 6 divided by 12 equals 1. All right. Okay, so that will tell us that the current is computed correctly. Now R1, the voltage through resistor 1, or the current through resistor 1, is V1, which is positive 6, divided by 2 is 3 amps. Let's do another example. And this one needs two voltages as well. So we're gonna have to set up two equations. So the original circuit is this, they're like connected to ground here. We have a source, 64 volts, we have a resistor, and then we have this circuit right here, a source and a resistor. You can, if you don't want to use nodal analysis for this particular case, you can change this into a equivalent source of a battery and a resistor, but we're trying to practice how to create equations with nodal analysis. Okay, so in that case, we simply set up our voltages and currents. So we're gonna know the first thing is pretty simple. This is always gonna be our reference volt equals 0 or ground. And then we're gonna have a voltage potential here and a different potential here, V1 and V2. So we need an equation for V1 and we need an equation for V2. So the first thing is realizing that I1 and I2, so I2 is right here and I1 is right here. So in other words, this is going to be my node V1 and this is my other current I. So I1 plus I2 plus I equals 0. So all the currents are leaving the node. And I equals 2, this is 2, but we don't know I1 nor I2. But we do know that I1, which is this right here, is the potential between, this is exactly what we did before. V1 is the source plus the voltage drop here. In order to get from 0 to the maximum potential, we have to go from the source and then the voltage drop that is dropped here. So I1 is V1 minus the voltage source divided by R1, because remember that V1 equals the voltage drop plus E. Okay, and here I1 is equal to the voltage drop to resistor 1 divided by R1. So we're just plugging in this equation here. For I2, it's going to be something similar, is voltage 2 divided by R2. And which one is I2? Is this guy. Except for, sorry, for the voltage through this resistor is voltage drop the resistor 2 divided by the resistance, which is 2. But this voltage right here is the difference between V1 and V2. Okay, so the first equation is going to be from V1 to V2. So V1 minus V2 over R2. Now we have the first equation. It's just a matter of bringing terms into the equation and reorganizing. And we have V1 times all that minus V2 times that equals 6 amps. Reorganizing the terms. Okay, so just take that into consideration because this term is just numbers. Okay, so rearranging the equation, we get this equation right here. This is number 1. Now for V2, we have another equation, which is start from the same point, the summation of voltages, I equals I2 plus I3. So this I is equal to the, check this node right here for V2, the current going to V2 and the current going to resistor 2, and obviously the current right here. So in this case, it's not I1 plus I2. No, in this case, we have one I going to the node, which is this capital I, and then we have two I's, two currents going outwards. So in that case, we do set up this equation. Because in other words, we would have I2 plus I3 minus I equal 0. Right? So this is the same as that. And just following up with below the equation, this I we know, which is 2. And then the current I2 is, now we start from V2, because this is what we want to find is V2. V2 minus V1 divided by R2 is this equation right here, plus V2 divided by R3 is this part of the equation right here. Now we just reorganize and we finally have equation number 2. So from equation 1, which we did before, and equation 2, which is we just solved for this, we can solve for V1 and V2. So V1 is 37.82, V2 is 32.73, and then we can just solve the currents the same way. The current through resistor 3 is voltage drop the resistor 3 over R3. We know how to do that. Voltage drop through resistor 3 is basically V2. And the same one for resistor, for the resistor node 2 is V1 minus V2 over resistor 2, and that's 1.27 amps. So this is how we solve for the voltages and the currents. So this is the third example. This one was a pretty good one because it's also showing how you solve for the nodal voltages. One last example on this nodal analysis, because I think that you get the point right now. So we're gonna have our common ground, which is right here at 0, and we're gonna have a V1 and V2 and V3 at this point, and this point, and this point, because notice that we have all the components of a node. We have currents through 3 branches. Okay, so we have 3 voltages and we're going to have 3 equations. Now, if in this case we have the 4th node here, 4 nodes, 3 equations. So in this case, it does apply the rule. So, which don't follow that rule because sometimes it's not very applicable. But for common circuits like this, where you have your nodes on the upper part, then it's pretty common. In this particular case, I guess we had, if we're counting ground, we're always gonna have 1. So 1, 2, 3, 2 equations, that's true. 1, 2, 3. Oh, it's because I was not counting ground. So the rule is always holding, except for I didn't count the node at ground. Okay, I apologize. So yes, we have 3 nodes, 2 equations. We have 3 nodes, 2 equations, and we have 4 nodes, and then we're gonna have 3 equations. Okay, let's solve this one. It has 4 nodes and 3 equations. So the first case is gonna be for voltage 1, and now we can just set up the equation directly. We know how to do that. So voltage 1 is gonna have this resistor, and that resistor, and this resistor. So the first thing is realize that voltage 1 is gonna have this mesh, or this loop. Okay, so the current, so let's see, V1 is going to be V equals IR, and I equals V over R. Okay, we're gonna set up by the currents. So V over R. Okay, so V1 over R, let's see. So this one is going to be current 1. This one is going to be, if we do voltage divided by 2 ohms, which is this, and divided by 2 ohms, which is this, and divided by 10 ohms, which is that. Okay, so this is telling us the voltage, the current going through here, the current going through here, and the current going through here. Good. Then we're gonna have that the voltage 2 going through this. So this is going to be minus because it's going towards V1, minus V2 over 2, because this is the V2 divided by 2. And we're gonna have V3 is connected to V1 through this resistor. So negative V3 over 10 ohms. Equation 1. So again, V1, we're gonna solve for current here. So, or in other words, we're gonna solve for voltage using the current going through the branches. And how do you use the current? By setting up this equation, V divided by R. So voltage 1 is going to be going through this branch, 10 ohms, which right here, this branch is 2 ohms, and this branch is 2 ohms. Okay, set up the equation, V1 divided by each of them, we have it. Then to V1 is also going V2 minus V1, so 2 ohms, 1 divided by 2 ohms, that's good. And then V3 is connected through 10 ohms. Excellent. So we have the first equation. Now we have to do the same thing for the other two loops, for this one and this one. All right, so let's go ahead and do V2. V2 is pretty simple. V2 is going to be connected to this resistor, to that resistor, and to that source. So first of all, let's go ahead and do from V2 to V1. It's going to be V2 over 2 ohms, correct? And it's going to be V2 to V3 is going to be V2 over 2 ohms, correct? That is V2. Now V1 is connected to V2 through 2 ohms, so negative um, V1 over 2 ohms. And V3 is connected to V2 through 2 ohms. So V3 is going to be negative V3 over 2 ohms. So if you realize, this is the same thing that we've been saying. This is V3 minus V2 over 2 ohms. And basically by breaking terms is V3 2 ohms minus V2 2 ohms. And V2 is going to go here, and V3 is going to go here. So we're reorganizing our equation that is simpler to write down and solve for the unknown variables. But this is the same thing we've been doing. V2 minus V1, V3 minus V2, V1 minus V2, etc. All right. And then last equation for V3, we have contribution of V1 through 10, V2 is contributing to 2, and V3 is all this loop. So let's go ahead and, oh, and don't forget that V2 has access to this source, so equals to 3 amp. Now V3 is this loop, so we're gonna have V2 minus V3, so V3 over 2 ohms right here, V3 over 4 ohms right here, and V3 over 10 ohms right here is positive. Now negative, because V2 is going to be 2 ohms. And V1 is connected to V3 to 10 through 10 ohms, this one. So I recommend that you set up the equations and see if you're getting the same thing. We should be getting the same thing. The only one that is getting the source is 3 amps. Well, what I mean is that the only one getting the source, which is 3 amps, is V2. So node 2 is the only one connected to the source. The other nodes are not directly connected to the source. All right, so just by solving that, you get, just write this down on your calculator. You're gonna have 1.1 volt of V1, negative 0.5 V2, negative 0.1 V3 equals 0, 1 V2, negative 0.5 V1, and 0.5 V3 equals 3. Actually, this one needs to go to this side so that we can solve it easy. And V3 is 0.85 minus 0.5 V2 and 0.1 V1 equals 0. So now we have three equations, three unknowns, and this circuit is originally this circuit. Okay, so even though it looks pretty complicated at first, we can set it up like this and it looks a little easier, where right here we have V1, we have V3, and we have V2, and we have V0. So 4 nodes, 3 equations.